Okay, so today we're going to start talking about instantaneous growth and decay. For this first one, we're not going to quite go to instantaneous yet, but we're going to cut down on the amount of time, at least, for our period. So the half-life of a certain substance is 24 years, and what we did previously was we said that X is equal to the number of half-lives. And then we knew that over that period of time, the amount of the substance decayed by 50%. So there was 50% left. So we said that M of X, so the amount of substance after X half-lives was our initial amount times 0.5 to the X. But the problem with that is that it assumes that you have 50 milligrams for 23.999999 years, and then bam, all of a sudden, when you hit 24 years, 25 milligrams of it just disappears, which we know isn't realistic, right? We know that it gradually decays. So we want to cut down on that amount of time to get a more realistic model, and talk about a function that tells us the amount of substance left after t years instead of after t 24-year period. So remember when we did this before, we had a way of figuring out the number of half-lives given the number of years. What did we do? So if I gave you like 4,000 years, you wouldn't plug 4,000 in as your exponent here, right? Because X is the number of half-lives. So how did we figure out what our exponent was going to be? So that was for our A, which we'll use in a minute. But this is just for our exponent. So if my... Well, let's just do some simple numbers. So if my half-life is 24 years and 48 years has passed, how many half-lives is that? 2, right? Which we got by doing what with the 48 and the 24? Dividing, right? So if you take the number of years and divide it by how many years there are in a half-life, that's going to tell you how many half-lives have passed. So number of years divided by the half-life. So we said X is the number of half-lives, and the number of years we're calling T, and then our half-life is 24. So you can get the number of half-lives by dividing the number of years by 24. So that's just telling you how many 24-year periods have passed. So using that, we can write our new function for the amount of substance left after t years by saying, okay, P of t is going to be the same as our function before, so 50 times 0.5. And then our exponent was the number of half-lives, which we can replace with t over 24. So we're getting closer, but we're not quite there because we don't want our exponent to be t over 24. We want our exponent to just be t, because the idea is that we'll get a decay factor that more accurately represents how much of that substance we're actually losing per year. So remember that t over 24 is just the same as 1/24 times t, right? You have t over 1, and you multiply by 1 over 24, you get t over 24. And when we raise exponential expressions to another exponent, we multiply the exponents, right? And so I can undo that process and say this is 50 times 0.5 to the 1 over 24, all raised to the t power, right? Because if you did that backwards, if we were going from 0.5 to the 1 over 24 to the t, we would multiply those exponents, and that's where we get that t over 24. So we just did that multiplication backwards. We just undid it. And so now we're going to need our calculator to figure out what a is. So go ahead and plug in your 0.5 to the 1 over 24, and let's round that to like 3 decimal places. Does it round to 2?
Yeah.
Okay. Good. To the t. So now we have a function of the form c times a to the t that represents this same decay, but it tells us yearly rather than every 24 years what's happening. So how can I figure out what percent the substance decreases by every year? So what am I asking for here? So to find, well, t is an amount of time, right? So we just want to know how much of the substance we're losing every year. So t is going to be 1 in that case, right?
Can you just set t to 1 or just multiply 50 by 1?
Okay, sure. So if t was 1, I don't know, what's 50 times 0.972? So then how would I figure out what percent of my substance I lost?
Divide that to 50.
Okay. So 48.6 divided by 50 is going to be 0.972. And I know that because I multiplied 50 by 0.972 to get 48.6, right? So everything you're saying is true. Like, we could figure out like how much we have left after 1 year, and we could use it to find that percent change. But there's an even simpler way, right? Remember that relationship I told you was super duper important and you should write it really big and put big boxes and stars? Oh, I think I put stars next to it. No, maybe that wasn't the one. Do you guys remember what it was? Had an A in it. Yeah, A equals 1 plus R. And remember, A is your decay or growth factor, and R is your decay or growth rate. So if we want to know what percent the substance decreases by each year, we're looking for our decay rate. So the rate at which we lose the substance each year. So A is 0.972. Which, if you forget that, is right here. I promise we won't use an A or an R in a place where it doesn't represent the A and the R in this formula. So when we're talking exponential growth, every time we use an A, that's your growth or decay factor, and every time we use an R, it's going to be your growth or decay rate. So equals 1 plus R, which gives me R equals negative 0.028. So it decays by 2.8% per year. And if we think about it, like that 97.2% represents like how much we have left, right? So like if I start with 100% of the substance, then after a year I have 97.2% of it left, which means that I lost 2.8% of it. Does that make sense? Okay, let's figure out how much of the substance is left after 16 years. So before we even plug a number in, should it be more or less than 25 milligrams? after 16 years.
More.
I'll have more because after 24 years, I have 25 milligrams left, right? That's what the half-life means, is that half the substance is gone after that amount of time. And so 16 years is less than 24 years, so I haven't lost half yet. So I should have more than 25. So we'll just evaluate our function for 16. So P of 16 equals 50 times 0.972 to the 16. Which is what?
31.7.
And that's in milligrams. Good. So now we want to go the other way. We want to know how long it's going to take for 10 milligrams of the substance to remain. What would you guys guess? Before we even do it. If it gets cut in half every 25 years or 24 years.
20.
So after 24 years, there's going to be how much left? 25. How much is going to be left after 48 years? 12.5, right? So probably something more than 40, well, definitely something more than 48, maybe not too far past 48. Does that make sense? So some of these you just want to, the only reason I'm asking you these questions is because if you have kind of a sense of how this works, then when you're solving these problems on a test, you can like just tell if it makes sense, like your answers. One of the big challenges with these types of problems and like interest problems, which we're about to get into, is just plugging them into your calculator the right way. And so like you can catch little mistakes in like punching them in and stuff if you can tell if your answer makes sense or if it's reasonable. So we want P of t to be 10. So we're solving the equation 10 equals 50 times 0.972 to the t. I'm going to come up here where I have more room. So this is where our solving of exponential equations comes into play. So what we were doing the other day. I'm going to start by isolating the exponential expression. So I have to divide both sides by 50. And that's going to give me 0.2 equals 0.972 to the t. And now we'll take the natural log of both sides. So we have natural log of 0.2 equals the natural log of 0.972 to the t. So then our log properties tells me I can bring that t down as my coefficient so that now I have multiplication instead of a variable in the exponent. So we have the natural log of 0.2 equals t times the natural log of 0.972. So we'll divide both sides by the natural log of 0.972 to isolate t. Over the natural log of 0.972. So go ahead and plug that in. One thing that people were getting a little tripped up on was when you hit the natural log button on your calculator, it like opens a set of parentheses. Make sure that you close that after the 0.2. Otherwise, like everything else you type is in the input of your natural log. So like it's going to look like this. What'd you guys get?
26.67.
Right, which is kind of what we thought, right? That it would be a bit more than 48. Is everybody getting that on their calculator? Okay. Like I said, these sometimes get a little funny, like when you're entering them, so that's something we'll practice today. Okay, let's talk interest. So we will, on the test, we will give you the compound interest formula, both periodic and continuous. However, we're not going to tell you what all the variables represent, so that's something you'll just have to practice and get used to what's what. So in the compound interest formula, we have a few things that affect it. So P is the principal, which is the initial balance. So the initial amount that's borrowed or invested. And then T is going to be the time in years. It's always in years. R is your annual interest rate. So when you see like savings accounts or loans or whatever, or credit cards advertised, that's what we call the APR. It stands for annual percentage rate. So that's what your R is. And we want to do this as a decimal rather than as a percent. And then N is the number, I'll write number of times compounded per year. So when we talk about compound interest, the idea is that when we compound interest, that's just saying they calculate your interest for a certain time period and then add it on to the balance. And then after that, you're paying or earning interest on that amount as well. So like it adds up, right? You're paying or earning. Let's just say earning. We don't want to get money, right? So after they add the interest on after, say, the first month or the first year, whatever your compounding period is, now you're earning interest not just on the original amount that you invested, but also on the interest that you accumulated in that first time period. So in general, if you are earning money, it's a good thing to compound more often because then they're adding more money for you to get interest on more often. So for example, like credit cards, they compound interest once a month. So every time they send you your statement, they add the interest on for that month. So the number of times compounded per year in that situation would be 12 because they do it 12 times a year, so each month. You can see down here what each of the terms means. Semi-annually means they compound twice a year, so that would mean N is 2. Quarterly is 4 times a year, etc. I won't expect you to know hourly and minutely, but you should know what N is for semi-annually, quarterly, monthly, and daily compounding. So our formula is A of T, which represents the balance after T years. So how much is in the account after all this interest has been added? And that is given by the principal, so your initial value, times 1 plus R divided by N. So what's in the parentheses there is basically like our A. It's your growth factor, which normally is just 1 plus R, but in this case we're dividing that annual interest rate into smaller periods. And then to the NT. So your exponent is the total number of times that that interest was compounded in that time period. So like if it's been 5 years and interest was compounded monthly, then your exponent ends up being 60 because there were 60 compounding periods in that 5 years, 12 per year for 5 years. So let's calculate some interest. In this case, we are given a principal balance of $1. We're investing it for 1 year. And our annual interest rate is 100%. So everything's gonna be a 1, except for the number of compoundings. And I should mention, this formula only works if you're not withdrawing or depositing any money during that time period. So like, it doesn't take into account like payments or anything like that. It's like you put money in an account and then it just sits there for T years. So semi-annually, whoops, is 2 times a year. So my N is 2. So in 1 year, I will have 1 times 1 plus 1 over 2 to the 2 times 1. And that ends up being $2.25. Before you get excited, nobody earns 100% interest. Don't go running to your banks. So you guys are going to calculate the rest of this table, except for this last line, which we'll do together. Please round to 4 decimal places. We don't normally do that with money, but there's a pattern here we want to see, and so that rounding to 4 decimal places will help. So go ahead and calculate the rest of those, except for the last one. Be what you got. Yeah? Look right. What pattern do you notice? Anything interesting? Yeah.
When the number gets huge, it like bubbles off.
Yeah, it starts to like level off, right? Almost like there's a horizontal asymptote there. Because we can see like as the numbers, as the N value gets bigger and bigger and bigger, like the difference between the amount that you end up with gets smaller and smaller and smaller. So like it levels off. What number do you think it levels off at? Close. It's E. Put E to the first in your calculator. Pretty cool, right? So the idea is that if you take this function, and think of it as a function of N. As N gets bigger and bigger and bigger, so remember we talked about end behavior. As our N value gets bigger and bigger and bigger, this tends towards the number E. And so that is why E is used when we do instantaneous or continuous growth or decay, because in all situations where the amount of time, the period of time that we're talking about gets smaller and smaller and smaller and smaller and smaller until it's so small that you can't even tell there's any distance in between them at all, we end up using a model that involves E. So if we go back to our general formula here, there's an R and a T and a P. If N gets really, really, really big, this gives us the continuous compounding formula, which is P times E to the RT when N gets huge. So that's just saying that if you were to graph both of these as with different values of N, as N got bigger and bigger and bigger and bigger, the graph of your periodic compounding function would get closer and closer and closer until it was basically identical to the graph of this continuous compounding function, which is the one that involves E. So if we calculate this for continuously, it would be A of t equals 1 times E to the 1 times 1, which of course is just E and rounds to 2.7183. So this is where that constant comes from, is by saying, okay, I don't want to pretend that a substance just magically poofs and loses half of itself after 24 years. We want to see more realistic things, and so we can cut things down into smaller chunks like we did with our half-life formula. We were like, oh, let's look at what it does over 1 year, but then that's still saying that it's the same for 364.9999 days, and then all of a sudden after, when we hit 1 year exactly, 2.8% of it disappears. So the idea that it happens continuously, not at specific intervals of time, which of course we know is more realistic, is where this constant came about. Is it's the constant that models that behavior, that continuous or instantaneous growth and decay. And tomorrow we'll use it for different types of functions, so for like our half-life and other types of growth and decay, but today we'll just focus on the interest formulas. So we have our compound, or our periodic compounding interest formula, and then our continuous compound interest formula, which is P e to the RT. And again, the variables mean the same thing, so P is our principal, R is our annual interest rate, and T is the time in years. So when it comes to figuring out which one of the formulas you should use, if you see the word continuous, use the continuous one. So it's really as simple as that. Like if it says that interest is being compounded continuously, go to the front of your test and find the formula that says continuous compound interest. So we're even labeling them for you. So periodic compound interest and continuous compound interest. So just look for that word continuously. If it's not there, it's periodically, and they should be giving you like quarterly or monthly or annually. If they say it's continuous, then just jump right to this. And this formula is actually working with continuous or instantaneous growth and decay actually ends up being a little bit simpler sometimes, because you don't have to calculate that A, the growth or decay factor. You just put your growth or decay rate directly into the function as R. So that's kind of handy. So let's do a couple calculations. So we want a function for the amount to which the investment grows after T years. We see, along with the word compounded, it says quarterly. It doesn't say continuously, so we know we're using the periodic interest formula. Our principal is $82,000. Our rate is 0.045. Time is going to be T, and then we need N. So N is 4 quarterly. So A of T equals 82,000 times 1 plus 0.045 divided by 4 to the 4t power. And typically we just leave, like what's in the parentheses, we just leave like that. This one works out kind of nicely. If you divide 0.045 by 4, like you get a terminating decimal, so we could actually evaluate that. But typically it's not quite that nice. So we just leave it as is and then just plug it all in the calculator at once. So let's evaluate A of 10. Is everybody cool with where all the numbers went and why they went there? Cool. So 82,000 times 1 plus 0.045 over 4 to the 4 times 10. So just plug that in your calculator all at once. And then this is where you might need parentheses around your exponent if you have the older calculator that doesn't jump up into superscript. So just to group that multiplication, 4 times 10, put this in parentheses. What do we get? 128. 278 and like 90 cents. Did you say 9.3?
903.
Okay. And typically, whenever money is involved, I mean, I'll give you rounding instructions on the test for all the problems except for ones that involve money. If it involves money, just round to the nearest cent, so to 2 decimal places. The only reason I had you do 4 in that last problem was so we could see the pattern of it approaching E. Okay, so let's figure out how long it takes our investment to double. So we want to end up with twice as much as we started with, which in this case would be $164,000. And so we're going to set our entire function equal to 164,000. So 82,000 times 1 plus 0.045 over 4 to the 4t. And we want to solve for t. So we're going to start by dividing both sides by 82,000. And this actually shows us something kind of interesting about the way interest works, which is that it actually doesn't matter how much money you put in. The only thing that determines how long it's going to take to double or triple or whatever is the interest rate itself. Because regardless of what that 82,000 was, the number on the left would have been twice as much. So when we divide, we would get 2. So like I wouldn't even have to give you necessarily the principal for you to figure out how long it would take for the investment to double at a certain interest rate. So to solve this, we're going to take the natural log of both sides. And then use our log rule to bring that 4t down as our coefficient. So natural log of 2 is 4t times the natural log of 1 plus 0.045 over 4. And then to solve for t, we're just going to divide by everything that isn't t on the right. So we're dividing by 4 times the natural log of 1 plus that whole thing. So t is going to be equal to the natural log of 2 over 4 times the natural log of 1 plus 0.045 over 4. And on this particular test, we are a little bit picky about rounding because we want to make sure you guys are putting these whole expressions into your calculator, not like taking the natural log of 2 way up top and then like writing down rounded values, because as you get further and further, those little bits are going to matter. So we don't want to round too early. We just want to round in the very last step. And I think, is this like 15.5? Is that what you guys got?
Yeah.
Anybody? Okay. Did anybody do it and like get something completely different than that? It's really half the battle is just pressing the buttons on these problems and making sure you have your parentheses in the right place. Be sure that your entire denominator is in parentheses. So that groups the 4 times natural log. Okay, so let's do a continuous one. So we invested $10,000 at an interest rate of 5.4% per year, and it is compounded continuously. So when I look at the word near the word compounded, I see continuously rather than monthly, daily, annually, or anything like that. And that's what tells me to use the continuous compounding formula, which is A of t equals PE to the RT. Somebody once pointed out to me that that spells pert, and now I can't think of anything but shampoo every time I write it. Like pert plus, that's what my dad used to use. So P equals our original investment, R equals 0.054, our interest rate as a decimal, and then T is just T. So that's our input. So we have A of T equals 10,000 times e to the 0.054 t. Good? So let's see how long it takes for that guy to double. So we want it to be 20,000. Divide both sides by 10,000, so you get that 2 again, and then e to the 0.054t. And this example kind of shows us the reason that we always use natural log to solve. Because all the realistic exponential growth and decay models involve e, using the natural log to solve exponential equations makes things work out really nicely when e is involved, and so that's why we just, as a convention, just always use that, because when we do these realistic models, the instantaneous growth and decay models, we end up using e every time, and so solving with the natural log just makes a lot more sense. So we'll take the natural log of both sides, and remember the natural log and e to the x are inverses of each other, and so they undo one another, which means on the right side we just end up with 0.054t. And then we'll divide by 0.054 on both sides to solve for t. So we get t equals the natural log of 2 divided by 0.054. I don't remember that one. I don't need your help.
12.836.
We'll call it 12.8 years. And that makes sense if we think about our previous example, right? The interest rate is higher here, which means that you're earning money faster. And so it would make sense that it doubles in less time than when we had 4.5% interest. Okay, so tonight you just have a worksheet, and in fact,